the Excel file Basics.xlsx. This is a file that's linked on the class webpage, and it's really there just for you to play around with and to refamiliarize yourself with some things that I know you've all seen before. But like most of us, if you don't use it, it starts to look pretty strange after a few weeks. So you may be in that position, and I know a lot of you are. It's been a long time since you've had calculus and algebra and trigonometry, and so this file is just here for you to play around with. We did talk about the answers to these simple problems in class, or we will do that. And I think I'll leave this to you just to refresh your memory. Large numbers, exponential notation or scientific notation, you should be pretty familiar with that. You've got a number like 597,000. This is 5.97 times, well, we have 1, 2, 3, 4, 5 decimal places, 10 to the 5th, or 5 significant digits here, 10 to the 5th. And so we can just write that as 5.97 times 10 to the 5th, 597,000 divided by 100,000, 5.97. When you want to write an exponential number in Excel, it's pretty easy. If we wanted to write the mass of the Earth, for example, 5.97, we know it's times 10 to the 24th. We put E24. And that's all we really need to do. We don't need to enter 24 zeros or 24 places. Now if I click on that, we'll see that number up there, and Excel can work with that number. So straight lines, you're familiar with that. You're probably saying, why is he talking about straight lines? Well, you know, again, it's one of those things where you haven't seen it for a long time. We're kind of going over basics. So this is a straight line. If you are a little foggy on some of these ideas, think about what the intercept is. Let's change that to a -1. And what happens? Well, all that happened there was that this straight line, the intercept is basically where this straight line intersects the y-axis, in this case at -1. Now if we change the slope from a +2 to a -2, that flips the line over. We still have the same intercept, got a straight line, and this is the slope, this is the intercept, this is the slope over here. Get in there and play around with it if you forget the significance of those parameters, those coefficients. This is the quadratic. I'm sure you have nightmares about quadratics, or have had in the past, probably, and certainly in algebra and trigonometry and calculus. You know, you run into this situation where you have to figure out what the roots of an equation are. So we have a quadratic equation up here. We've got coefficients defined as 4, 3, and -1 for A, B, and C, and we get something that looks like this. The roots are simply the locations of the points on the x-axis where this function intersects the x-axis at y equal 0. So this would be one root at -1. This would be another root at 0.25. So all we've done is really just solve this equation here. So get in there and play around with it. You can change the coefficients around. We changed that from a -4 to a +4. Now we don't have any roots. The equation doesn't intersect the x-axis. So, okay, allometric growth. This is something else that you should be familiar with. It's you know, we should probably refer to this as exponential growth or exponential decay. It just depends on the sign of the exponent here. The porosity-depth relationship has a negative exponent, and that's because the porosity decreases from some maximum value, and it kind of converges asymptotically towards 0 depending on compaction and rock lithology and structure. So we can get in here and change this around. This is phi 0 is basically turns out to be the intercept in this equation. If the porosity is only 40%, and that makes the intercept here, and we see it descending towards 0 again. We could change the value of lambda, and you'll see that the rate at which the porosity decays is not quite as rapid as it was with a lambda of 1. Excuse me. Logs, there's not much that I can do in here, but we'll talk more about logs in class, and I'll just pass over these. If we take a look at problem 14, this is something we will talk a good bit about. This is the Gutenberg-Richter relationship. It's also referred to as a frequency-magnitude relationship. It's a very often used relationship in earthquake seismology. It's a pretty simple one, obviously. A straight line, a linear relationship between the log of the number of earthquakes of magnitude, in this case magnitude 0 and higher, is almost up to 8. So 10 to the 8th. What would that be? Let's see. Whoops, excuse me. 10 to the 10 to the 8th. So we have 100 million. So we're likely to have 100 million earthquakes of magnitude 0 and higher. Of course, those aren't really felt earthquakes. We can use this relationship predictively if we have good measurements over a range of magnitude 3 to magnitude 5. We may want to know what the possibility is or the recurrence interval is for a magnitude 6 or 7 or 8. So a relationship that you'll see more of in class. Trigonometric expressions, again, if you haven't seen them for a while, just think about them, read the book, refresh your memory on what a sine is, a cosine, tangent, this arc length relationship here between the length of the arc, the subtended angle, and the radius of the circle, something else that comes in handy. And then, be able to distinguish these curves. Looking at these diagrams here. This is the cosine. This is the sine. This is the tangent. The tangent blows up. Why does the tangent blow up? The tangent blows up because it's the ratio of the side opposite over the side adjacent. And as theta gets closer and closer to 90 degrees, y gets closer and closer to r, x gets closer and closer to 0. We're dividing a number by a number which is approaching 0, so the function blows up. And we're back to this, not back to it, but we're looking at the sine function and the sine of nx. This is a question that is given to you if you aren't really sure what that means. This value in here tells you basically how many complete cycles of the sine wave you're going to have in 360 degrees. So 3 cycles, 1, 2, 3, 6 cycles, 1, 2, 3, 4, 5, 6. So again, something for you to play around with. It's up to you. We'll be running into these relationships in problem sets, on exams, and again, it's called Basics.xlsx. Have a look.